Okay, today we are diving into something called esterification. I know, it sounds a little scientific, maybe a bit complex, but trust me, this is the chemistry behind some of the best smells you know and love. I mean, have you ever really thought about it? You pop open a container of fresh strawberries, or you start peeling an orange, and that amazing smell hits you. What is that? Is it just one thing, or like 100 different things all mixed together? How does a banana smell so unapologetically like a banana? Well, it's not some kind of magic trick. It's actually just chemistry. And the stars of the show are these organic molecules called esters. Think of them like tiny little chemical fingerprints. They're the reason pineapples, apples, bananas, you name it, have their unique signature scents. All right, so let's dig in. What exactly are these things, these esters? How do they create this natural perfume that's all around us? Let's get into it. Okay, so here's the textbook definition for you. An ester is what you get when an acid and an alcohol react. A good way to think about it is like a chemical handshake. A piece from one molecule and a piece from another combine, and poof, you get something totally new. And that whole process, that recipe, that's what we call esterification. All right, let's put on our imaginary lab coats for a minute, because now we're going to walk through the actual recipe, how a chemist would create one of these amazing smelling molecules right from scratch. So how do you actually make one? Well, you start with two main ingredients, something called a carboxylic acid and an alcohol. But here's the thing, you can't just, mix them in a bowl and hope for the best. It's not going to do much. They need a little push. And that push is heat. But you run into a problem. You can't just stick the beaker on a hot plate. Why? Well, because a lot of these ingredients, especially the alcohol and the ester you're trying to make, are pretty volatile. That just means they love to turn into a gas and float away. Poof, they're gone. So chemists have this really clever setup called reflux. You heat the mixture, sure, but there's a cooling tube on top. So as the vapors rise, they hit the cold glass, turn back into liquid, and drip right back down into the pot. It's awesome. It lets you heat things for a long, long time without losing any of your good stuff. Okay, so we've got our ingredients, we've got our heat, but even with all that, this reaction is so slow. Like, we could be waiting for days. To really get this party started, we need a chemical matchmaker. We need a catalyst. And for this recipe, our catalyst is just a few drops of concentrated sulfuric acid. So how does this matchmaker work? Well, basically, the acid gives one of our ingredients, the carboxylic acid, a little boost. It makes a certain part of that molecule suddenly look really attractive to the alcohol. So now the alcohol molecule can't resist. It just zooms in, attacks, and bam. The connection is made, and our ester forms way, way faster.
But wait, there's a catch, and it's a pretty big one. This whole reaction, it's a two-way street. Just as the acid and alcohol are making the ester can break back down into the acid and alcohol. It's called a chemical equilibrium. It's like the reaction is constantly moving forwards and backwards at the same time.
So after we let our reaction cook for a while, what we have in our flask is, well, it's kind of a messy soup. We've got the ester we want, sure, but it's mixed with leftover ingredients, that acid catalyst, everything. And that's where the next big step comes in, the great purification. So the very first thing we have to do in this big cleanup, what chemists call a workup, is get rid of all that leftover acid. And to do that, we use something you probably have in your kitchen right now, sodium bicarbonate. Yep, baking soda. And baking soda is seriously perfect for this job, for 3 reasons. First off, it zaps that strong sulfuric acid catalyst we added. Second, it turns any leftover acidic gunk into salts. Now, these salts love water, but they hate our ester, which is key. And third, and you really got to pay attention to this part, it produces carbon dioxide gas. You can kind of think of it like using soap to get grease off your hands. The baking soda basically grabs all that acidic stuff and makes it so it can be washed away with water. Our ester, though, is more like oil. It doesn't mix with the water, so it gets left behind nice and clean. Okay, so remember that carbon dioxide gas I just mentioned? Well, when you're doing all this washing, you're usually shaking everything up in a sealed glass funnel. And all that gas starts to build up, which leads to a really, really important question. Yeah, you have to vent that funnel to stop it from basically turning into a chemical bomb. Seriously, if you don't let that pressure out, it can shoot the stopper out of the top like a champagne cork and spray chemicals all over the lab. So you do this simple little move. You flip it upside down and open the tap for a second.
It's a tiny step, but it is absolutely critical for staying safe.
Okay, so let's just do a quick rundown of the whole cleanup. You've got the baking soda wash to kill the acid, then you do another wash with just plain water to get rid of any leftover salts or alcohol. After that, you toss in a special drying agent. It's basically a powder that acts like a super sponge, soaking up every last drop of water. And then finally, you just carefully pour your nice, clean, dry ester into a new flask. All right, we are so close. What we have now is our crude ester. It's pretty clean. No more acid, no more water. But to get it really, truly pure, there is one last, kind of elegant step we have to take. And this last step is called distillation. It's all based on a really simple idea. Different liquids boil at different temperatures. So you heat your mixture up. Your pure ester will turn into a vapor at its specific boiling point, float up and over through some glassware, and then cool back down into a super pure liquid in a completely separate flask. All the other junk with a higher boiling point, it just gets left behind. And there you have it. After all of that work, we've got our pure product. So we measure it, and let's say we got an 82% yield, which for a lab experiment like this, that's actually pretty good. But it's not 100%, is it? And in chemistry, it almost never is. This is probably the #1 question every single chemistry student asks. Where did the other 18% go? Well, there are a few main culprits. First, remember that two-way street reaction? That equilibrium means some of your product was always turning back into the ingredients you started with. Then there's just physical loss. Every single time you pour something from one container to another, you leave a little drop behind. It all adds up. And finally, our cleaning steps are good, but they're not magic. They're never 100% perfect. And that brings us right back to where we started. We've made this pure ester. Now we can finally open the flask and, carefully take a whiff. That fruity, sweet smell, that's the molecule we just built, floating up into your nose and fitting perfectly into tiny receptors, just like a key sliding into a lock. And if you change the acid or the alcohol you started with, you make a different shaped key, and you get a completely different smell. So it's pretty amazing, right? From just a few chemicals reacting in a flask, you get this entire complex world of aromas. It really makes you think, if you could go into a lab and build any smell you wanted, a scent that no one has ever smelled before, what would you create?